Welcome to the second video on the binomial expansion today. So we're going to be having a look at how we can use an easier method than having to get out the Pascal's triangle each and every time we need to do a difficult expansion, and we're going to link that into combinations and permutations, which in plain English means we need to be thinking about how many ways could we pick a certain number of objects given a certain number of choices of those objects. So for example, how many ways would there be of picking 3 items if we had 5 items to choose from? It all links in to that, and using those ideas we can apply that to work out the coefficients of the binomial expansion much easier on a calculator as well, without having to go back to the triangle. So let's have a look at the warm-up questions before we start proper. There's 4 to have a go at. Question 1 is introducing the idea of a factorial, which is very important, and we'll use that today. Try these yourselves first. Once you've tried them, press play and see if my answers match yours. So let's have a look now at question 1. So we've got a factorial, which we're told it's a product of a positive integer, n, and all of the positive integers below it. And it's written as n factorial. So for example, 4 factorial is 4 multiplied by 3 multiplied by 2 multiplied by 1, which comes out to be 24. So for A, working out 3 factorial, that's going to be 3 times 2 times 1, which is 6. 5 factorial is 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. Now I'm just going to make a little note here, not that you need it to answer this question, but notice, if you do, that 5 factorial is 5 multiplied by this, which was 4 factorial. So you can think of 5 factorial as being 5 multiplied by 4 factorial. And that would equal 5 times 24, which should be 120. Part C, 5 factorial divided by 3 factorial. That's going to be the answer to part B, which is 120, divided by the answer to part A, which was 6. 120 divided by 6 is going to give us 20. But again, I want you to consider it like this. You could rewrite 5 factorial as 5 times 4 times 3 times 2 times 1, and 3 factorial is simply 3 times 2 times 1. Seeing these patterns will help you in terms of answering the questions with more deeper understanding. So on the top and the bottom we can cancel out the 1s, the 2s and the 3s, so you can see why it's 20, because you're just left with 5 times 4, which is 20. So it's not about answering the question, we already knew it was 20, but I'm trying to show you the links as to why it drops out as 20, and these patterns will be helpful in future. Number 2, how many different ways can you arrange the letters A, B and C? So imagine the order matters. So I'd suggest do this systematically and do it alphabetically. So the first way you could do it would be A, B, C. Still keeping A at the front, we could also have A, C, B, and that's the only ways we could have it where A is at the front. So now we've exhausted all options if A is at the front. We now need to think about if B was at the front. So we can have B followed by A and C, or we could have B and then C and A. And those are the only 2 ways you could have it, with B being at the front. So now we've done the A's, done the B's, let's try it with C at the front. So that could then be C followed by A, B, or we could have it C followed by B, A. Just be careful to actually answer the question. It says how many different ways can you arrange these letters. So to do that, wouldn't actually be answering it. So to answer the question, there's 1, 2, 3, 4, 5, 6 ways of arranging these letters. Question 3, using your answer to question 2 or otherwise, how many different ways can you arrange the letters A, B, C and D? So adding another letter into the mix here. So what I'm going to do is imagine D just tagged on the front of what we had before. What we had before from question 2 was ABC, ACB, BAC, BCA, CAB, and CBA. So just imagine the D just being popped on the front of all of these. So that would be 6 ways there. So it's going to be the same idea if we had A at the front, B at the front, or C at the front. It's just going to be different letters, but there's going to be 6 arrangements for each. So if we had A at the front, we could have it so that it's B, C, D. Keeping A and B at the front, we could have it so that it's DC. And that exhausts all the options where B is at the front, assuming A is at the front for all of these. So I'm going to try and show you where this pattern comes from. So next we need to have C at the front. 2 ways of if C was at the front, assuming A obviously is at the very, very front. We could have AC and then either BD or DB. And finally, if we then have D after the A, then we could then have BC or CB. So you can see here that there would be 6 ways of doing it. Let's try now with B's at the front. So we could have A, not B because it's there, CD, or ADC. Or we could have C, AD, CDA, or we could have BD, AC, or BD, CA. Again, another 6 ways there. And finally, doing it this way that I've done it, thinking of it where C comes first. There'll be 6 options for where C comes first. So starting with A next, it could be BD, or we could have CADB. Now B coming next, we could have CB, AD, or CBDA. Then finally, with the D coming after the C, we could have CDAB or CDBA. And again, there's 6 ways of doing that. So the total here is 24 ways. But before we move on, I want you to just consider the relevance of the 24. We've got 4 objects, and we're thinking of all the possible arrangements of 4 objects. 24 is 4 factorial. If I go back to question 2, we had 3 letters being arranged in every single way we could think about. 3 ways. 6 is 3 factorial. So when the order matters, it's factorial. So if you've got 4 items, you want to list all the different ways they're going to be listed in, that would be 4 factorial. If you had 10 items, you wanted to know the total number of possible arrangements of those 10 items, it would be 10 factorial. So this idea of factorials is going to tie in later on. Question 4, an easier one. Simplify minus 2x all to the power 5. That's going to be minus 2 to the power 5 and x to the power 5. So minus 2 multiplied by itself 5 times will give us minus 32, and x to the power 5 is just x to the power 5. And that concludes the warm-up part of the session. So now let's move on and discuss Pascal's triangle with a bit more depth. Before we do that, just returning to combinations for a second. So imagine now we had a choice of the letters A, B, C, D and E. How many different ways are there of choosing 3 letters to place in each of the 3 boxes below? So how many different ways? I mean, picking 3 letters, but also where the order of those letters within these boxes is also relevant and important. So the order matters as well. So for each selection of 3 letters, there'd be 6 different combinations of how they could be ordered. That's from warm-up question 2. We saw that when the letters were A, B and C, there's 6 ways of ordering it when there's 3 letters picked. But how many different combinations of letters could we pick if we've got A, B, C, D and E to choose from? Just going back to warm-up question 2 there. So if the letters picked were A, B and C, these would be the different orderings, so 6 different orderings. But like I've said, how many ways of picking 3 of these letters of a total possible 5 are there? Well, there's actually 10 combinations of 3 letters that can be picked. We could pick ABC, ABD, ABE, ACD, ACE, and ADE. These are all the combinations of letters that could be picked that include the letter A. And each one of these combinations within itself will have 6 different possible orderings. So that's all the combinations if we're picking the letter A. So what about if we're just picking some combination of B, C, D and E? Well, we could pick BCD, we could pick BCE, and we could pick BDE. That's now all the combinations of letters that include B without including A. So here we've got all the possibilities of having A and B including in the pickings of these 3 letters. So if A and B weren't included, that leaves just C, D and E, which is the 10th and final combination of letters. So there's 10 combinations of letters, and each one of those combinations of 3 letters would have 6 possible orderings. So because each of these groupings has 6 different orderings, the orderings are called permutations. So when we're interested in the different orderings, they're called permutations. When we're not interested in the order, but just which ones have been picked, that's combinations. So what this is saying is, in total, for the 5 letters, A, B, C, D and E, there are 10 lots of 6 unique permutations. Each of these 10 combinations has 6 different orderings. So in total, there's going to be 10 multiplied by 6, which is 60 different ways that these letters could be picked and ordered into these boxes. Therefore, the number of permutations, where the order matters, of these 3 letters chosen from 5 letters is 60. That's a hell of a lot. However, what if the order of the letters in the boxes didn't matter at all? How would that change things? So, for example, if the letters we chose from A, B, C, D and E were A, B and C, and we're saying that the order didn't really matter, then the following permutations, the following orderings are all equivalent, because it wouldn't matter which one we pick. They're all effectively the same, because each one of the orderings includes A, B and C. And in this scenario, let's just imagine that's all we care about, what letters we've picked. So there's 10 combinations of letters that can be picked, which we worked out from before, which are these combinations here. And so if we're not bothered about these 6 different permutations for each combination of 3, we can take the 60 total permutations and divide through by 6, because instead of 6 permutations we're interested in, we just want 1 of those permutations, and that will do us. And so the total combinations is just 10. So if the order doesn't matter, there's only 10 combinations of 3 letters we can pick from 5, whereas if the order did matter, there'd be 60 different combinations of these 3 different letters we could pick from the 5 letters in total. So that's the technical side explained. Now for the good news. The upshot of all this is we can use combinations and factorial notation to expand binomial expressions. For larger indices, it's much quicker than using Pascal's triangle as well, which is the great thing about it. The number of ways of choosing R items from a group of N items is written as below. It's N, big C for combinations, or you can think of it as choose R. So it's often read as N choose R. And it's written as a column vector looking expression, in brackets, N on top, R on the bottom. It's calculated by N factorial divided by the product of R factorial and N minus R factorial. Your calculator does this for you though, which helps massively. So, like I've said, we say N choose R for N CR, and it's sometimes written without a superscript and subscript, and just written as N CR. So what we had earlier was the idea of 5 letters, A, B, C, D, and E. How many ways was there of choosing 3 letters from those 5 letters in total? So here we had 5 to choose from in total. So that was 5 choose 3. And the button for this is above the division symbol. So you press 5 for total number of items, Shift C, choose 3. So on the calculator it says 5, bold C, 3. And we had familiar it was 10 combinations. So let's see what this gives us. 5C3 was 10. Now what you don't need to worry about at all for this stage of the A level is this NPR button. The P stands for permutations. And so the total number of different arrangements of 3 letters being picked from 5, where order matters, was 60, wasn't it? So if we try 5P3, we get 60. But for the binomial expansion, we're only interested in NCR. And so NCR actually essentially generates the coefficients of Pascal's triangle for us, which is absolutely fantastic. So because of that, we can now represent Pascal's triangle in terms of combinations. So looking at it in that way, the first 4 rows of a triangle are as follows. So that's 0, choose 0, which I can show you here actually. So 0, shift, choose 0 is 1. This one here is 1, choose 0, which is 1. This one, 1, choose 1, is 1. If I skip down to this row here, where we've got 3 things, this is if you were doing a cubic. So for example, a plus b cubed. This tells us the coefficients of those. So the first one, 3, choose 0. You'll soon see choose 0 always gives us 1. And the next one would be 3. 3, choose 2. The next coefficient here is 3. And finally, 3, choose 3 is 3. So if you were to try these and match them from the coefficients you got from the first lesson on the binomial expansion, you'd see that these combinations match exactly the coefficients from Pascal's triangle. So rather than having to do the triangle yourself, it's just far easier just to get the calculator to do the hard work for you. Generally speaking, the rth entry in the nth row of Pascal's triangle is given by this. So it's n minus 1, choose r minus 1. So we knock 1 off the row you're after, and you knock 1 off the entry in that row you're trying to find. And in column notation, it's written as n minus 1, r minus 1. A few warm-up examples, just to get you used to using your calculator. So first of all, calculate 7, choose 3. So get your Classwiz ready, and I'll show you how to do it from scratch again. So type in this 7 first, then shift divide for the C, then press 3. And you get here that it's 35. So in other words, 7 choose 3 gives us 35. B, 9 and 5, that means 9 choose 5. So typing that into our Classwiz, we can press Shift Divide in a moment. So 9 Shift Divide for the C, then 5, that gives us 126. And part C of question 1, calculate the 5th entry of the 8th row of Pascal's triangle. Now I could never remember how to do these, but essentially you knock one off each. So just to remind you, here it is. This is the way of working it out. And so n minus 1, choose r minus 1, where n is the nth row you're talking about. So we want the 8th row. So 8 minus 1 is 7. So we're wanting to do 7, pick r minus 1. We want the 5th entry, so 5 minus 1 is 4. So 7, choose 4, will give us the 5th entry along on the 8th row. So we can actually, if you've got a combination already on your calculator, you can press back and forward to just edit the numbers. So 7C 4 is 35. I now invite you to just check from your first lesson if that is the 5th entry on the 8th row of Pascal's triangle, and I'm sure you'll find that it is. So I've got my fancy looking honeycomb one over here. So if I go down to the 8th row, 1, 2, 3, 4, 5, 6, 7, 8, and then the 5th one in, 1, 2, 3, 4, 5, you will indeed see that the 5th entry along the 8th row is 35, like we calculated it to be. So moving on. Question 2 of the worked examples. So given that 3017 equals 30 factorial over 17 factorial a factorial, we're asked here to work out the value of a. So for this one, what we need to do is to remember how we defined the factorial and the combinations. So going back to that, n choose r was n above r in this form, which equals n factorial over r factorial multiplied by n minus r factorial. And so now that we know that, we can apply it to this case here. And so we've got everything we need just to work out what a is. And so that's going to be 30 factorial. Using this definition here, we're picking 17, so that's 17 factorial, and n minus r in this case is 30 minus 17, which is 13 factorial. And so it must be the case that a has to be 13. So to solve that one, we're just using the knowledge of the n choose r function linked to factorials. For b, we need to prove that n choose 3 equals n minus 1, n minus 2 over 6. To do this, it's crucial that we know how this links to factorials. So n choose 3, that will equal n factorial over 3 factorial multiplied by n minus 3 factorial. Now we need to remember what the factorial function does. We start with n and then we multiply by each and every positive integer below n. So n factorial means n times n minus 1 times n minus 2 multiplied by n minus 3. I'm going to do a few here on this line so you can see the pattern of what's going to happen. times n minus 4 times dot 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 until we get down to 3 times 2 times 1. Whereas we need to link this to n minus 3 factorial. Well, 3 factorial is 3 times 2 times 1, which is 6. So we can write the 6 there. Then n minus 3 factorial means we start at n minus 3 and multiply by every integer below that. So the next integer below n minus 3 is n minus 4, then n minus 5, and so on, all the way down to 3 times 2 times 1. By writing it in this long-handed way, you can see the pattern much clearer. There's going to be lots of cancellations on the top and bottom. We can cancel the 1, the 2, the 3, everything in between, and of course the n minus 4. And so the only thing we're going to be left with, once we cancel the n minus 3 as well, of course, almost missed that, that would be foolish, is n minus 1, n minus 2 over 6, which is precisely what we wanted to prove all along anyway. And so that's this question sorted. So let's generalize what we've found here. So the binomial expansion. So a binomial expression is just a polynomial with two terms, for example 2x plus 1 or 3x plus xy squared. If we want to expand binomials in brackets to a positive integer index, in other words, expand brackets to a power which is a whole number and positive, we can use a binomial expansion. So this is the general binomial expansion. So a plus b raised to the power n, where n is some natural number, a whole number, 1, 2, 3, 4, 5. You have a to the power n, then n choose 1, a to the power n minus 1b. So the power of a goes down and the power of b goes up. Now, sometimes in class and in these videos, you might see me rewriting a to the power n differently. It's equivalent what I write down, but sometimes I'll write a to the power n as n choose 0, a to the power n, and sometimes I'll even include b0, just so you can clear as crystal see the link. And so it starts n0, n1, n2, n3, n4, all the way up to the end, which is n choose n. The power of a goes down until it reaches 0, and the power of b goes up until it reaches the same power as what the power of the brackets have been raised to. So sometimes I'll rewrite what you see here, and I'll switch a to the power n with this, and I'll switch out b to the power n with this below it. It's exactly equivalent. What I'm writing down is a longer way of doing it, but I sometimes do this just so you can see crystal clear the pattern. n0, n1, n2, so on. an goes from n minus 1, n minus 2, whereas b goes from power 0, in other words 1, so you can just forget the b, to power 1, power 2, all the way up to the power n. So just a few things to mention. This here, where we've got the brackets, remember n choose 1, whoops, or n choose 2, generally you can define it as this. n choose r is n factorial over r factorial multiplied by n minus r factorial. Your calculator does all the legwork for you. For example, if you had a plus b to the power 4, which written in the long way is a plus b written out 4 times, then the term a b cubed would occur 4 choose 3 times. 4 choose 3, by the way, is 4. I'll just show you here. So 4 shift divide C3 is 4. And so a to the power 4, a plus b, sorry, to the power 4, we get a b cubed 4 to the 3 times. This is because you can choose b 3 times from 4 brackets in this many ways. You've got 4 brackets with b in, you're choosing just 3 b's. When the expansion is simplified, the ab cubed term becomes 4 choose 3 ab cubed, which is 4 ab cubed. I've got an illustration to show you about this picking and the combinations. So imagine you've got these brackets a plus b, a plus b, a plus b, a plus b. So first of all, we might want to pick the first 3 b's in the first 3 brackets, multiply them together, along with the a from the last one. That's one way of doing it. We could pick this combination of b's, the first, the second, the fourth, and multiply this a by them to get the next ab cubed. Or we could pick the first b and the last 2 and multiply this a by them to get the third ab cubed. And last but not least, the final way of doing it, we could just pick the last 3 b's and multiply these last 3 b's by the very first a. So together, that's how you get your 4 ab cubes. So this is just the stuff going on behind the scenes. To be honest, a lot of this you can just rely on your calculator for, but for the deep sort of understanding, this might be interesting to you. If you just want to crack on and see how it works in terms of using your calculator, I've got a couple of worked examples for you to show you, but actually it's pretty simple indeed. So worked example 1. Use the binomial expansion to find the expansion of 2 minus 3x all to the power 4 in ascending powers of x. Generally speaking, when we do the binomial expansion, the last thing here goes ascending. This here is descending. So I did warn you about my long way of writing it out. So I'm going to do it here. So if you want to just skip what I'm doing in the first term, you can, but I just want to show you, then you can take the stabilizers off the bike if you like and just go for the quicker way. So 2 minus 3x to the power 4, interestingly and importantly, it's power 4. So we start with 4, pick nothing. We start with the first thing to the same power. So 2 to the power 4, and then minus 3x to the power 0. The minus 3x to the power 0 just means it doesn't really exist at all. Next along, we have 4 choose 1. Each time, this one decreases its power by 1, so we have 2 cubed next. Whereas for minus 3x, that's going to go up a power each time. So this one is now power 1. 4, 0, 4, 1, now we have 4, 2. 2 cubed goes down again to 2 squared, whereas the minus 3x goes up 1. It was power 1, it's now going to be power 2. 4, 0, 4, 1, 4, 2, now we have 4, choose 3. The 2 squared goes down to 2 to the power 1, and the minus 3x squared goes up to minus 3x cubed. And finally, we get so we're choosing the same number of items of what we have all together. If you think about it as well, if you've got 4 teddies, you want to pick 4 of them. There's only one way of doing that. You pick them all and run off on holiday. So 4 choose 4 is always going to be 1, as is 4 choose 0. There's only one way of picking nothing from 4 items. You just simply pick nothing and go away. So anyway, going back to what I'm trying to say here. So 2 to the power 1 reduces to 2 to the power 0, and the minus 3x eventually goes up to 4. And the total index, it'll always be the same as the power which you're raising your brackets to. 4 plus 0 is 4, 3 plus 1 is 4, 2 plus 2 is 4, and so on. So I'm just going to show you how to do this on the calculator. You'll eventually get to a point where you realise that actually your first term is just the first term raised to the power of what the bracket's been raised to. This will just be 2 to the power 4, which is 16. But I'll show you on a calculator regardless. So 4, choose 0, multiplied by 2 to the power 4 multiplied by minus 3 to the power 0. 16. I'll leave the x out because I can't input the x in the calculator as I can the same way as a number. So we just need to remember to put the x's on the end if they exist at all. Here they don't. What I'm going to show you now is once you've done one on your calculator, you can just edit what you've got quite easily to generate the next one. So the next one here, let's underline actually, this one is 16. The next one we're going to have a look at is here. So we just edit what we've already got. So 4, choose 1 now. So scroll back, delete the 0, replace it with 1. For power, toggle on the 4, delete the 4, replace it with 3. And for minus 3x, we now have power 1. So delete the 0, replace it with a 1. So we have minus 96. So the next one, whoops, won't be a plus. It's actually going to be a minus 96x. The next one we're going to have, 4 choose 2, 2 squared, minus 3x all squared. So again, just editing it out like I said you can do. So 4 choose 1 becomes 4 choose 2. Delete the power 3, replace it with power 2. And the minus 3 to the power 1, replace the 1 with a squared. And that gives us 216. So it's plus 216 x squared next. Then this is going to be a minus. So I'm going to put a minus in. But I'll show you on the calculator, just so you're in no doubt that it is a minus. So 4 choose 3, so go back and edit the 2 to a 3. The power of 2 is now reduced down to a 1, so delete this 2, replace it with a 1, whereas the power of the minus 3 is increased from 2 up to 3. So delete the 2, replace it with a 3. Press equals, and we get minus 216. It's going to be minus 216 x cubed. And finally, 4 choose 4 is just 1, 2 to the power 0 is 1, minus 3 to the power 4, that's going to be 81, so we have 81 x to the power 4. Now I've underlined these just so you can see how the technical looking bits reduce to the simpler bits, but obviously you don't need to put that in your answer, that's just for illustration purposes. So your final answer is just this, without the underlined bits. So if you want to, you can take these off. And that's the answer in a less colourful way. But his answer, still all the same. The last one, we're going to use the binomial expansion to find in ascending powers of x the first 3 terms of the expansion. So importantly, it says the first 3 terms. So the hint here is don't waste your time doing the whole thing. We want ascending powers of x. The x term is the last in the binomial, so we're fine. This will naturally ascend. And so this here, the first 3 terms, 2 minus a quarter x to the power 5. The first term will be 5, choose 0, 2 to the power 5, minus a quarter x to the power 0. Second term, 5 choose 1, 2 to the power 4, minus a quarter x now goes up to the power 1. Then 5 choose 2, 2 to the power 3, minus a quarter x squared. And yes, it would continue, But remember, the first three terms are just this one, that one, and this one. So we don't need to fiddle around and bother with doing it all, unless you want to waste your time in an exam situation where time is also crucial. So working this out. So here we go. So we want 5 choose 0. Multiplied by 2 to the power 5. Then to work out the coefficient, we obviously just drop the x. So it's minus a quarter. Fraction button. I'll put into the power 0. Now this is just going to be 2 to the power 5. It's just going to be 32, but as I warned you, I sometimes do it the long-handed way so you can see the pattern much clearer. At least I think you can anyway. If you happen to differ with me, that's absolutely fine. If you don't need to do it this way, you can just write down 2 to the power 5, 32 straight off. That's absolutely fine. The next one, 5 choose 1. So toggle back, alter this 0 to a 1. Alter the power of 2, sorry, from a 5 to a 4. And it's minus a quarter now to the power 1. That gives us minus 20. So the next thing is minus 20x. Whoops, not a plus, but actually a minus 20x. And the last one, we've got an even power of a minus, so this will be positive. So now we're going to have 5 choose 2. 2 to the power 3. Multiplied by minus a quarter squared. So the coefficient of x squared is 5. So we end up with 5x squared. And that's our final answer. So, yes, technically, if there is other stuff after it, it does go on if you like, but that's all we need to do for the first 3 terms. 1, 2, 3, we're done. Don't need to worry about anything else at all. So now it's over to you guys. These are suggested exercises, starting on page 164, going on to 165. It's exercise 8C. I just want you to try questions 4, 5, 6, and 7. Check your answers immediately after doing each question, and consult me if you're stuck in any way, shape, or form. Keep plugging away, keep working hard, don't get behind, and I'll see you very soon. Thanks again.